Polymers. They're everywhere. Toys, clothing, wire insulation, transport, and so much more. Today, however, we'll focus on their significance in one of the world's most important areas, the kitchen. But what even is a polymer anyway? A polymer, derived from the Greek words for many in parts, is a large molecule made by linking repeating small units, known as monomers. Examples of monomers could be ethene, 1,2-ethanediol, and tetrafluoroethylene. The joining together of these small units is a process known as polymerization. The joining of two units forms a dimer, three a trimer, and so on. But we don't want to have to draw out every unit for polymers consisting of many repeating units. So we draw brackets around a repeat unit with a subscript n to show that there are n amount of a repeat unit. Now, how do we classify them? There are several ways of classifying polymers, the first of which I'll be talking about was first suggested by Wallace Carruthers. In 1929, he proposed that polymers should be classified based on the chemical reactions employed in polymerization, which is what you may most already be familiar with. He sorted polymers into condensation and addition polymers. Condensation polymers are those prepared from monomers where the reaction is caused with loss of a small molecule, typically water. One family of polymers you'll have come across that fits into this classification would be polyesters. On the other hand, addition polymers are those formed by the addition reaction of an unsaturated monomer. So an example would be polyalkenes such as polyethylene, or more commonly known as polyethylene. The next classification method is just a slight alteration to the first. P.J. Flory suggested that classification should be emphasised on the mechanisms of the polymerization reactions. So, he reclassified polymerizations as either step growth or chain growth reactions, each of which roughly correspond to condensation or addition in Carruthers' scheme, although there are a few exceptions to this. But how do these reactions work? In step growth polymerization, all monomers and already grown chains have reactive sites. In this video here, we can see that the golden beads, where one bead is a monomer, can join together at either end to form dimers, then join another one to form a trimer, and so on. These trimers can then add on to already grown chains, such as other dimers and trimers, to form a longer chain polymer. Here is another way to look at it. Think of this white grid as a field of people, with each dot being a person representing a monomer. The two hands from each person represent the reactive sites. In a short time interval, some of the people are asked to join their hands with their nearest neighbours. This represents polymerization, and the polymers here are very short-chained. After longer time intervals, longer chains of people are formed, and eventually, chains of people can join other chains too, representing the formation of long-chain polymers. Conversely, in chain growth polymerization, monomers are added one by one at the end of a growing polymer chain. The monomers involved are unsaturated, and the active site, which is either a radical or an ion, needs to be created, unlike in step growth where the monomers already have active sites. There are multiple mechanisms for chain growth polymerization, depending on the initiator used to generate this active site, but they all share three common steps which you may recognise from the synthesis of haloalkanes from alkanes. Initiation, which involves the creation of active sites, propagation, which involves the rapid addition of monomer units to the active site, growing the polymer, and finally termination, which involves the neutralization of the active site by direct quenching or transfer of the active site. First off, we have free radical polymerization. Now, an ideal initiator would be one that is stable at room temperature, as to not thermally decompose, but break down to form reactive radicals when heated or irradiated with UV light. Initiators such as benzoyl peroxide or AIBN are primarily used. Here, the two carbon-nitrogen single bonds in AIBN undergo homolytic fission after heat is applied, generating 2 moles of initiator radical. This radical then reacts with our monomer, in this case ethylene, to generate the active site and reactive polymer chain. Then we have propagation, where the polymer chain adds onto another monomer unit, extending the chain and moving the reactive radical, the active site, toward the end again, ready to repeat the same process. This would in the end create polyethylene, a polymer I'll go into more detail about later on. Now, the propagation will continue until something acts to quench the reactive radical. This is termination, and there are 2 main mechanisms for it. First, there's chain combination, where 2 reactive polymer chains join together, and then there's disproportionation, where a proton is abstracted from another grown polymer chain, creating one polymer alkane and one polymer alkene. The other two mechanisms, cationic and anionic polymerization, are very similar to free radical polymerization in that they have the three common steps of initiation, propagation, and termination. But there are a few key differences. For example, the initiator and generated active site are different for both. For cationic, Lewis acids, which are electron pair acceptors, such as BF3, are ideal initiators and the generated active site is a cation, whereas for anionic polymerization, bases such as butyl lithium are used as initiators to produce an anionic active site. So, to summarise, chain growth polymerization would look a little something like this, where we treat each golden ball as a monomer, all joined to one end of the polymer chain, with the generation of a new active site after each monomer is added. So, that's pretty much the basics for polymers, their classifications and polymerization mechanisms. Before I mentioned that polymers have a wide range of applications, and the kitchen is one of many places where polymers are incredibly useful. One very practical use of polymers is in non-stick cookware, such as non-stick pans. Non-stick pans are typically coated in a polymer known as polytetrafluoroethylene, PTFE for short, or Teflon. In 1938, Dr. Roy Plunkett attempted to synthesize a gaseous refrigerant by reacting tetrafluoroethylene, TFE, which is the monomer present in PTFE, with hydrochloric acid. He checked the pressure on a full cylinder TFE, but found that it had no pressure. Instead, a small amount of a slippery white substance was in its place. The substance was found to be PTFE, later trademarked as Teflon by the DuPont company. The general mechanism for the formation of PTFE from its monomer TFE is shown here. As we can see, the polymerization of TFE follows a free radical polymerization mechanism, where peroxide initiators are activated by forming alkoxyl radicals. These radicals then add across the carbon-carbon double bond of TFE to form a carbon radical. More monomers add across and create more carbon radicals in many propagation steps, and eventually the joining together of the polymer chain radical and another radical, either another polymer chain radical or an alkoxyl radical, terminates the growing polymer, forming PTFE. Let's now talk about what it is about PTFE that makes it so useful. Due to fluorine being so electronegative, the carbon-fluorine bonds are incredibly strong and require lots of energy to break in order to react, making PTFE one of the most stable and inert plastics. This is good as we don't want our non-stick pans reacting with any of the foods we put on it. The outer sheath of fluorine atoms also lowers the surface energy greatly, giving PTFE a low coefficient of friction and non-stick properties. Surface energy is defined as the energy required per unit area to increase the size of the surface. So, to increase the size of the surface, there must be some energy input. The amount of energy input required relates to the strength of attractions between the pan coating and anything that goes on it. Although you would think that PTFE is polar due to the highly polarized carbon-fluorine bonds, it isn't, and it can only interact via weak London forces with other molecules. This is because PTFE is linear, meaning the overall dipole moment is cancelled out to zero, making PTFE non-polar and unable to have permanent dipole-dipole interactions or hydrogen bonding with other substances. So, PTFE is unable to form strong bonds with substances such as water, meaning there is little energetic reward for the substance to break bulk bonding and spread out to increase interactions with the PTFE surface, giving PTFE non-stick properties. Next, the melting point of PTFE is very high. It melts at 327 degrees Celsius. This probably seems quite unusual since previously I talked about how the polymer chains only have a weak London interactions. However, since the fluorine atom's substituents are very large, steric repulsion prevents PTFE from forming a planar zigzag conformation, like polyethylene. Instead, it has helical conformation, a bit like DNA. Steric repulsion arises when two bulky atoms or groups are closer to one another than their atomic radii allow. Hence repulsion occurs, which increases the energy and therefore decreases the stability. Forming this helical conformation reduces the steric repulsion, since adjacent fluorine atoms won't be as close to one another. This helical morphology is conducive for PTFE molecules to pack like parallel rods. It's a result of this close packing that increases the strength of interaction between PTFE molecules, increasing its melting point. This is, of course, essential, since pans will have to endure very high temperatures so that we can cook whatever's on it. otherwise the PTFE coating would melt and come off into our food. Another very useful polymer in the kitchen is polyethylene. It has many uses as a component in electronics, fibre optics, toys, bin liners, and especially in the kitchen and things like cling film milk containers. So, unsurprisingly, polyethylene is the single largest volume polymer worldwide, with global production estimated at a whopping 84 million tonnes, or about 76 million kilograms, in 2014, a 3.8% increase from the preceding year. Polyethylene was discovered by accident in 1898, where Hans von Pechmann observed a white waxy decomposition product upon heating diazomethane, which was analysed by his colleagues who found that it contained CH2 repeat units, and thus termed the material polymethylene. They did not investigate any further into this polymerization reaction, and it wasn't until 1930 where Carruthers, who at the time was interested in the stability of linear alkanes, isolated linear alkanes generated by condensation reactions with up to 70 carbons in the chain. But this condensation approach to PE synthesis was industrially impractical, so it wasn't until 1933 that British company Imperial Chemical Industries actually discovered, as opposed to observed, polyethylene and was able to commercialise what was later to be called low-density polyethylene. The main two types of polyethylene are known as LDPE and HDPE. LDPE is prepared from gaseous ethylene under very high pressure and high temperatures, in the presence of a free radical initiator, meaning PE is a chain growth polymer. This produces a long and short branched polyethylene chain. HDPE, on the other hand, is manufactured at lower temperatures and lower pressures by a process known as Phillips process, which uses a Phillips catalyst. The product formed is a non-branched polyethylene. Polyethylene is incredibly inert. The non-polar CH bonds and saturated CC covalent bonds means that the amount of chemical reactions that polyethylene can undergo is severely limited. This is useful since we don't want LDPE cling film reacting with the food that we wrap it in, nor do we want HDPE milk bottles reacting with our milk. Since LDPE is highly branched, it is difficult for it to pack closely together with other polymer chains, meaning it cannot form hard, stiff, crystalline arrangements and is instead very flexible. This flexibility is easily observed in cling film. Conversely, since HDPE lacks branching, the polymer chains can pack closely together, resulting in a highly crystalline material of high strength and moderate stiffness. So, this makes it useful in things like milk containers, since the material used needs to be able to withstand containing kilograms of liquid without having to be used in excess. Now, polymers are clearly very impactful in our lives on a day-to-day basis. However, there are plenty of downsides to them. Marine life such as sea turtles may mistake plastic pellets for food. Upon consumption of the pellets, the turtles become too buoyant to dive properly for food, and consequently they die. Other than causing visual pollution, polyethylene plastic bags that end up as litter can often cause damage to animals and plants too. Although lots of polymers such as single-use plastics get discarded properly into landfill sites, available land is in short supply, and since most plastics are non-biodegradable, they will take many years to degrade. However, it isn't all doom and gloom. Recycling of scrap PTFE into fluoroadditives, which can then be added to plastics, inks, oils, etc., to impart fluoropolymer-like properties such as reduced wear rate and friction. HDPE can also be recycled. Upon collection, the plastic is sorted and cleaned to remove any unwanted debris. The plastic then needs to be homogenized so that only HDPE will be processed. If other plastic polymers are present, this can ruin the recycled product. HDPE is then shredded and melted down to further refine the polymer. It is then cooled into pellets, which can then be used in manufacturing. The problem with recycling has to do with economics. It's not generally cost efficient to recycle highly used polymers such as polyethylene, since the recovered material has a low intrinsic value. This is because the popularity of these highly coveted plastic polymers is due to their ease of manufacture and consequent low cost. An alternative method to tackle the problem of waste polymers is to make them degradable. However, by making them degradable, we then worsen the properties that made them so useful in the first place, such as their durability. They must also have a reasonable lifetime. Plastic bags cannot start to degrade to any extent from the moment they're produced, otherwise they won't be usable. So, the best solution would be to make the degradation triggered by something like UV light. To conclude, properties of polymers result in them having a vast number of applications. And in the kitchen, they let us fry eggs without the hassle of them sticking to our cookware, and they also make it so that we don't have to lug around large and heavy milk containers that would otherwise be made of something else such as glass. However, they clearly have an adverse effect on the environment, and research into more cost-efficient polymer recycling or polymer disposal is vital.